This video is all about enzymes. So first I'm going to start talking about what exactly enzymes are. They're proteins, which means they're made up of amino acids. And enzymes' function is that it's actually going to speed up chemical reactions inside of an organism. So these are like biological cheat codes to helping us sort of manipulate the way nature forms and breaks down certain molecules. And I'll get into more detail about that in a second. Because enzymes do speed up chemical reactions, we call them a catalyst. And it's really important to note that connecting it back to the laws of thermodynamics, enzymes don't make more product and they don't make more energy than you would get from that natural chemical reaction. So all it's doing is it's taking a reaction that might take 1,000 years and it can complete it in less than a minute. So it just allows biological processes to run really smooth inside of your body and any other organisms, and it gets ATP to your cells and muscles fast enough to where it's usable. Because if it took you 1,000 years to break down your food, you obviously would not be able to survive. If an enzyme could take something and create more energy than natural, that would be impossible and against the first law of thermodynamics, so it is not true. Please don't confuse that on the exam. Enzymes, they just help make things occur faster. They do not create more energy or product than would naturally happen. In this video, I'm going to focus on two major types of reactions, catabolic and anabolic, and how enzymes play into that, and also how energy and our laws of thermodynamics relate to these concepts so we can sort of tie everything together, and hopefully you will see how a lot of these things that I've been talking about connect. I'm going to start with catabolic reactions, and I'm going to give you some facts about these to hopefully allow you to understand what all catabolic reactions have in common. First thing is that catabolic reactions are when you take a complex molecule and you break it down, releasing energy. Because all things in the universe favor chaos or being broken apart, this is what we call a spontaneous reaction, or something that is going to happen naturally anyway. It's just, how long that takes really just depends on the type of reaction. So that's where enzymes will come into play with speeding those reactions up. These reactions are going to release energy into the environment, and just note that spontaneous doesn't mean instantaneous. So in nature, these could take a really, really long time. An example is that a car will spontaneously rust over the course of, decades, and that is a spontaneous reaction where something is being broken down, but it does take some time. An example that we're going to focus on for a catabolic reaction or pathway inside of a cell is going to be cellular respiration, and also another example we've already discussed this year is hydrolysis, which is actually taking polymers or complex biological macromolecules and breaking them down or breaking them apart into monomers. And that process actually releases some heat and energy into the environment. Let's take a look at a graph that is going to display all of the information I've just talked about in a concise and visual form. So for this example, I'm going to talk about cellular respiration in a very simple way. I'm going to draw our chart. So on the X, we're going to have time. And on the Y, we're going to have free energy, which is basically how much energy is in our reactants and our products that is usable. So I'm going to go and write that. So because this is a catabolic reaction, our reactants, or what goes in, is actually going to have more free energy than the products what comes out. And in this case, our main reactant is going to be our glucose molecule, which is C6H12O6, pretty complex, and it has a lot of potential energy, because remember, the more complex something is, the more potential energy it has. So what we want to do is we want to take that potential energy of glucose and release it and turn it into a form of energy usable by the cell. However, you probably know that when you have sugar on your, just sugar that you keep in your kitchen, it doesn't just naturally melt or spontaneously combust. You have to put energy in order to break the bonds between all of these molecules. And that amount of energy has a name, and it's called activation energy. So think it's the amount of energy that is required to activate this particular reaction. So that is going to require input. So you can see activation energy is displayed here with this sort of hill-like structure. And I drew a red line just to show that this is the starting potential energy, or the amount of potential energy in this glucose. So we're actually going to have to put energy in, and then we'll be all the way up here, and just kind of like a roller coaster takes energy to get to the top of the hill, it's going to take some energy to get this particular glucose molecule to break. And then we'll start releasing energy into the environment. So this maximum PE is basically equal to the amount of energy it takes to break the bonds between this glucose. So I've just kind of measured the activation energy here, so you have a visual that this is approximately how much more energy has to go in before we can actually reap the benefits of all the potential energy stored in this glucose. So now what's going to happen is, through a series of reactions in cellular respiration, which I'll talk about later, we're actually going to release that energy into the environment, and this glucose is going to get ripped apart. So we take that solid glucose and we tear it apart, and that in turn is going to be releasing heat energy, and also energy will be used from that glucose to make ATP in the cell, which is the usable form, which is great. So remember, the second law of thermodynamics states that whenever you convert energy from one form to another, some of that energy is going to be released and increase the entropy of the universe, which in this case is going to be this heat energy is released, which is going to excite the particles around the cell and around you, which is technically increasing the entropy. So obviously our glucose has been changed throughout this process. So it's actually no longer glucose, and is going to be turned into carbon dioxide, which we are currently breathing out, which has a lot less potential energy, because all that energy from the glucose is now kind of lost to the environment. And what we're left with is a gaseous carbon dioxide, which has a lot less potential energy stored in its bonds. So where did the energy go between here and here? Well, we can see that no energy is created or destroyed. It's just going to be transformed from chemical energy into this energy that our cell is now going to use and our body loses as heat. So it's not that that energy disappeared, it's just changed form from our glucose to our carbon dioxide. So you're probably asking, hey, where's the enzyme coming into play here? I thought you said this video was about enzymes. Well, this particular reaction would take so long naturally that enzymes are going to kind of help speed this reaction up. And how they do that is they actually lower the amount of activation energy required to break that glucose apart. So I'm going to draw a line that is going to describe this reaction with a enzyme involved. So because an enzyme can just kind of grab the glucose and start breaking it apart, it's actually going to lower the amount of energy required to get this reaction started. And by lowering that, it's just going to speed up the process. So just like a roller coaster would take longer to climb this higher hill than this one, it's just going to take less time to get to where we need to start this particular process. So one of the most important things to note here is that the amount of energy released does not change with or without the enzyme. The only thing that's affected is the amount of time it takes for this process to occur. The fact that enzymes lower the activation energy and speed this process up is the key concept to take away here. Let's take a look at what exactly a catabolic enzyme, or an enzyme that breaks something down, how it actually works and what it looks like. So this is an enzyme, and it's the best I can do in terms of drawing it as a cartoon. So the whole entire red blob I've drawn is the enzyme, and this particular area here on the inside is called the active site. The active site is where the substrate or the reactant or what's going into the enzyme binds. So the active site is sort of like a lock and key with the substrate, meaning that it's very specific. That particular substrate is going to fit into that particular enzyme, just like the key to my house is going to fit the lock to my front door, but it's not going to work well with my neighbor's house, for instance. So each enzyme has its own particular substrate and its own very unique active site that will bind to that substrate. So here we've got our substrate, this green ball. It's going to go into the enzyme and it's going to come out the product. So the enzyme is actually going to take that substrate and it's going to rip it apart because this is a catabolic enzyme, or it breaks things down. So you can see the substrate fits perfectly right into that active site. And now the enzyme has taken that substrate and ripped it apart. And because this is a catabolic reaction, our products are going to be less complex than the reactants, which you can see this ball altogether is more complex or more ordered. And this product down here is going to be less complex and way more disordered. So we've actually increased the entropy here. And also, because this is catabolic, it's going to release energy or release heat, and it's also going to create some ATP, or at least help create ATP. So this is a catabolic enzyme, or something that breaks things down. So let's take a look at the flip side, which is an anabolic enzyme and reactions. So the main anabolic reaction we focus on is photosynthesis. Because I've already kind of explained catabolic in detail, I'm going to kind of speed through this one because it's literally the exact opposite. So when I draw the diagram or the graph for this reaction, you'll notice that it literally looks like I've just flipped the catabolic graph and chart. In this case, the reactants, or what goes into the reaction, is actually going to have a less potential energy than the products. So in this case, carbon dioxide is going to go in and glucose is actually going to be created or come out. So in this case, you can see we have activation energy again. It's just the amount of energy that has to go into the system to take carbon dioxide and beef it up into a glucose. So you can see we actually overshoot slightly how much potential energy is stored in glucose. We go over. And that's because in this process, we actually create a molecule that will break apart into and create a glucose after it's broken apart a little bit. So just like in our catabolic reactions, enzymes are going to speed this up, and they're just going to lower the amount of energy required to make this glucose. So it's going to speed up the reaction as well, the exact same way. So remember, enzymes aren't going to help make more glucose. They're just going to make glucose faster than this would actually occur naturally. So you can see that the difference between where we start and finish is the same with or without an enzyme. It's just with one, that activation energy is lower and we're going to get to our product faster. And this is an anabolic reaction because instead of releasing energy to the environment, this takes energy because we're going from less complex to more complex. So just like it would take energy from me to go from less complex, Legos scattered around my floor to a more complex Lego structure, I have to put energy in to make that happen. So in this case, an anabolic reaction actually requires energy to occur. And where does the energy come from in this particular reaction? Well, we know photo means light, and synthesis means to make. So we're actually using energy from the sun or sunlight to synthesize a glucose. So sunlight is actually being stored in the bonds of the glucose. So we're taking energy and we're storing it instead of breaking something down and releasing energy to use it. And all the enzymes are going to do is lower that activation energy, so this happens faster. So what's different is the enzymes used in photosynthesis are actually anabolic enzymes, which are the builders. So let's take a look at that. So just like catabolic enzymes, these enzymes are going to have an active site where the substrate binds, or substrates in this case. So in this case, the pieces, or the chaotic, less energy, less PE substrates, or the reactants, are going to go into the active site, and they're actually going to come out more complex and put together, or more ordered. So for instance, in photosynthesis, carbon dioxide, which is a gas, goes in, and a product, glucose, which is a solid and much more complex, comes out. So this requires energy to happen. So these enzymes actually are going to use energy or use ATP in order to build something more complex from something less complex. Just like it takes energy to order anything else, cleaning my room, building Legos, building a table out of pieces. This process requires energy, and that is the main difference between your anabolic enzymes and your catabolic enzymes. In another video, I'm going to explain the optimal range of enzymes and also what happens when enzymes go outside of that optimal range.